Now let's talk about the interaction between light and matter that we talked about, that is very strong. So there's reflection that can happen. That was one of the things that can happen when light hits an object. And specular reflection happens when light hits a surface that is very smooth. So nothing is perfectly smooth. That's impossible, because at the end of the day you will end up with little lumps of matter which are called atoms, so you can make that uniform. But if these bumps are not too big, and the idea is that if the size of those bumps is smaller or of the order of a wavelength of the light that hits this, then when you send light rays here and they hit the surface, they get bounced off the surface in a very neat way. Two light rays parallel, they get reflected in a parallel fashion. And there is a very simple rule that tells you in which direction it is going to be reflected. If you call this the angle of incidence, which we usually measure from the perpendicular to the surface. So this is a surface, say this is a mirror. Then that light ray, this could be a laser beam, right? Gets reflected, and the angle that it makes with the normal is the same. We call it theta of reflection, and the law of reflection says that those angles are the same, are identical. But that's not always going to be the case. In fact, the reflection of light off your bodies, maybe a part of your eye, will be diffuse, which is the other kind. Which is when the irregularities on the surface are bigger than the wavelength of light. Remember that this number, you can take it to be something like 500 nanometers. So any irregularity bigger than that will produce, running out of space here. So this is very regular surface now. So when two light rays, say, come in parallel, one is going to hit this bump here, so the reflection might happen that way, but this one hit this top of the bump, and then that one gets sent that way. So the reflection goes in all possible directions. That is what allows, actually, most people in this room to see this guy over here, because the light reflected by his shoulder is shooting out in all possible directions, right? If it was a mirror, that would be if it was all made of glass, that would be a little different. So that's diffuse reflection. So a mirror is a device that has been made, that has been polished, or the way it was made, ensure that the irregularities were of that order of magnitude for the wavelength, typical wavelengths of light. So what you see there is the photons coming out of an object that is at the arrow. I'm going to show it to you again. So there is a mirror here. They hit the mirror and they bounce off. The angle of reflection is equal to the angle of incidence. So that's a photon here going in that direction. When it hits the mirror, this line, the perpendicular line to the direction, and the reflected photon, they make the same angle, this one and this one. Now what are those lines that we're projecting backwards? and that seem to intersect at a point behind the mirror. Why are they important? Let me leave that picture there. They're not photons. There is no photons behind the mirror. You should be clear about that. No photon can penetrate or pass the mirror. This is your object here, and you shoot a photon that way. It gets reflected. And because of the very organized way in which light gets reflected off a mirror, all of the light rays, as you can see in that, when they get reflected, the reflected light rays seem to be coming from the same point. What does that seem to be? Why do they seem to be coming from that one point? Well, what your eye does is, if there is an object here and it's emitting light in all of these directions, your eye is sort of like an elongated device with an opening here and the retina on the back. So it has to be oriented with the light rays that are coming in, right? So there's two things that allow your eye to tell where the object, allow you to infer the source of the light rays, because you interact with the light rays. You don't interact with the object. You don't really know where the object is. You have to infer that, right? So what happens is that the light rays are divergent as they enter the eye. There is a lens here that focuses them on the retina. And one thing that tells you where the object is that you assume that it's right in front of your eye. It has to be, otherwise the light would not reach your retina. So you know that if you receive light, there has to be an object along this line. How far is the object? There's two things that allow you to do that. One is how much you have to adjust the lens to get a sharp image of the object here. A faraway object allows you to see it with relaxed crystalline lens, but a close object causes stress in your eye because you have to squeeze the lens in your eye to be able to focus that sharply on the retina. So that's one clue as to the distance. The other clue is that you have two eyes, and each eye is going to have to be oriented in a different direction to receive light coming from that object. So that angle, if the object is really close to your eyes have to go like this. If the object is far away, your eyes can be parallel. So that gives you any information about where that object is, right? So what I'm trying to say is that from the light rays that are coming in your eyes, you can deduce, by following straight lines, you can deduce where the source of that light is. So if you have an eye here, or two, and you get light coming in from that direction, you will infer that there is an object. The source of that light rays is over there. If your eye, of course the other eye here, I'm making it deliberately elongated, receives light, same frequency and so on, same intensity, then you would infer that the object is here. And with that information, you know where the source is. At least you think you know where the source is. So when you stretch these lines, when you project the light rays, the physical light rays back, if they intersect behind the mirror or the lens or whatever device that you have there, if it's only the projection, you call this thing a virtual image. Because there is no light rays actually intersecting there, right? It's a perception thing. But your eyes cannot tell the difference, of course, because all you receive is the photons. So if you do the geometry for 2 of those light rays that get reflected off the surface of the mirror, you project them, you see where they intersect, you will find a very simple rule about where the image of the object is. This is the mirror. You have a source. This is the object here. You can take 2 light rays, as I said, any 2 light rays. You carefully draw the angle that it makes when it hits the mirror. You reflect it at exactly the same angle. You take a second light ray. Again, you do measure that angle. You do the reflected one precisely with the same angle. You connect this, continue these 2 lines. They will intersect at this point. This is where the image is. And that image is going to be along the perpendicular line to the mirror that goes through the object, and the distance that the image is from the surface of the mirror is equal to the distance that the object is from the mirror. So the distance of the image to the mirror equals the distance of the object. It's very simple to do it with the geometry. Use whatever angle alpha this is. This is going to be alpha 2. If this is beta, that's going to be beta also. If the angles are the same, then they're going to have to intersect at the same distance, this one to this one. So a mirror, a flat mirror, a plane mirror, is the first device that we have now, that we have discussed, that produces an image of an object, right? You just put a plane mirror, an object in front, there will be an image form of that object. So for an observer over here, you will see the object. Depending on where the observer is, you can see the object because there is photons going that way, and you get those. But you would also get some of these photons coming from this direction, and it makes you think that there's something else there. So you can see both the object and the image. Now things get a little bit more complicated when you have more than one mirror. Let me show you the case with 2 mirrors, and they're making a 90-degree angle between them. So that's one mirror, this is the other one, 90 degrees in between them. The light hits this mirror. Then it can, some of the light rays can hit the other mirror. After they bounce here, they can bounce over here too. And they go this direction. So some of the light rays that a person would observe here will seem to be coming from that direction. So you think that there's something there. Some of the light rays seem to be coming from that direction. That's another image. Some of the light rays seem to be coming from this direction. That's another image. So the same stream of light rays coming out of that object can get reflected in different ways and produce images at different locations. So I won't go into the details of that. It's not that important. But just to tell you what, it's not that hard to find where those images are, because you're simply using this rule. Right? If you have a mirror and an object in front of it, you know where the image of that object is going to be. If there is a second mirror, that image of the first one could become the object of the second mirror. And then you will have another reflected image over here. And depending on the configuration of the mirrors, that could become the object of this mirror back here, and so on. So you can get several bounces of the mirrors. And at each bounce, that corresponds to a new image. Every time a light ray bounces off a mirror in your configuration, that will produce an image. All right?